Can you hear me at the back? Give me a wave. Can you hear me at the back? Thank you, everybody. So good afternoon, everyone. My name is Matt Woods. I am the Chief Data Scientist here at Amazon Web Services. Basically means that I get to come and talk to smart people, such as yourselves, about any high-performance computing-related needs that you might have or any workflows that you're running. My background is in HPC and in data analytics. I worked on the human genome before joining Amazon, helped set up the next-generation DNA sequencing pipeline back in Cambridge in the UK. And in the time that I've been at Amazon, which is probably getting on for 3.5 years now, we've seen the story of HPC change significantly. So when we first launched Amazon EC2 way back in November 2006, we spotted very quickly that customers started to use this programmable utility computing environment to run analytics scale-out workflows, basically. So they were able to take this utility computing environment, program it, deploy it very, very large scale. And I could talk about IOPS and interconnects and all those things all day long. But what our customers really found early on was that this utility general purpose platform that we had with EC2 was really starting to remove the constraints around their high performance workloads. So it's starting to change the way that they were thinking about the problems that they were trying to solve and the questions that they were trying to ask of their data. And there was a very large, and it continues to be a very large, pent-up demand for high-performance computing. Because traditionally, in the sort of old traditional infrastructure world, almost all HPC is resource constrained. You have to try and figure out, based on queue lengths, based on the capacity that you have available to you, either if you're lucky enough to have access to a supercomputing center, or if you have the cluster under your desk, you have to try and figure out what questions can I fit into my hardware? What questions can I fit into the resources that I have available to me today? And what we found very early on with EC2 was that customers started to pick up that those resources started to melt away in the cloud. They found out that they didn't have to worry about fitting their problem into the resources that they had available. They were able to start scaling out their problems. They were able to start thinking more in terms of, well, given how much infrastructure I need, do I need to be able to solve a problem? So very early on, we saw scale-out systems start to appear. These were relatively straightforward. They would sometimes have queues involved. They would sometimes not. They were built around SQS, and they were basically for embarrassingly parallel traditional scale-out systems. So workloads that decompose very easily into small lumps of compute, which you can then just throw up onto the cloud, orchestrate with a queue, wait a couple of hours, and your results come back in. But increasingly, what we started to see was we heard from customers that they basically wanted more and more power. So they wanted to be able to not just run scale-out workloads, but be able to scale up the questions that they were going to be able to ask on the physical hardware. Now, everything we do at Amazon is driven by that customer feedback. Give you a sort of insight into how we operate. We basically, before we write a line of code for a new service, we'll write the press release for what that service is going to be announced. It's PR-driven development. And we'll write the FAQ, which is real questions that we collect from customers. And the basis of this is that everything that we develop is driven by the questions and the requests that we get from customers, such as your good selves. And we heard over and over again that although the scale-up workloads were operating well, and that was allowing the researchers, the academics, the industrial HPC users to be able to start to scale up, they also wanted to be able to run more tightly coupled workloads rather than just embarrassingly parallel. So they were asking basically for more CPU firepower. They were looking to move beyond just scale out to more tightly coupled parallel processing. So we heard that loud and clear. And in November, I think a couple of years ago, we launched cluster computing instances. So these are specific instances which run on EC2, or an EC2 instance type, which are specifically designed for high-performance computing and have a couple of really, really nice features. So the first is that we start to pull back the curtain about which CPU you're running on so that you can optimize for your CPU. So CC1, the first generation, runs on Intel Nehalem processors. There's quite a lot of firepower in them. But more interestingly than that, we also deployed those onto a specially designed high-performance network. So this is a 10 gigabit bisectional network, which means that all of your nodes in a cluster can talk at 10 gig all at the same time. So in addition to that, we also wanted to be able to allow customers to control the physical location of the virtual machines that they were spinning up in the Amazon data centers. So we introduced the concept of placement groups. And this allows you to spec out a placement group and EC2 will try and launch your instances on hardware which is closely located within the data center. Couple that with this high-performance 10 gig bisecting network, and you can achieve some pretty impressive scaling requirements. But customers, HPC customers, always want more, and we kept hearing the same thing. We want more CPU firepower, more CPU firepower. So in November at Supercomputing last year, we announced the second generation of cluster compute instances, which we imaginatively titled CC2. .8 extra large is the full API name. And these are running Intel E5 Sandy Bridge processors. Very, very high performance, and nice little backstory. We actually had them deployed in production, available for API and high performance use about 6 months before they entered the channel for all of our other partners. We had a great relationship with Intel. We do a lot of work with them. And they did ask us to try and hide which CPU it was. Any idiot could figure it out. But then about 6 months later, we pulled the covers off, and surprise, you're running on Sandy Bridge, which is then called E5. So these offer very, very high performance. You can optimize for the sort of performance benefits that you can see with an Intel E5, compiling for AVX and things like that. They are deployed on the same high-performance 10 gig E network that all our cluster compute instances are. And the day before we announced them, we were able to run a benchmark, not against the whole fleet. We had some private beta customers that were using the infrastructure, but around a certain amount of the fleet. It was around 17,000 cores, if I remember rightly. And that benchmarked in at 240 teraflops. And we submitted that to the top 500 list, and we ranked in, this is last year, in November, we ranked in at number 42. So this is the world's 42nd most powerful supercomputer, deployed on demand and available for anybody to use. So that really was an epoch in the arrival of high-performance computing in the cloud. That this was actually the fastest performing Ethernet-powered supercomputer in the world, deployed on an elastic infrastructure that's available to everybody. So 240 teraflops, yeah, you can do a lot of damage. One of the problems that we have with HPC is that we are now in general availability. So anybody can jump in, and so we can't renew our benchmarks very often because we have so many customers actually using the infrastructure. So this is the most up-to-date benchmark we have, unfortunately. In addition to asking for additional CPU, more power, we've also heard from customers that they wanted additional IOPS. They wanted to be able to deliver additional read and write performance. And so in about 6 months ago, I think, we started to introduce the concept of provision throughput to the elastic block store devices, where you could reserve the capacity your application needed to specific block stores. EBS, if you're not familiar, if you're new to AWS, is a persistent block store. You can format it in any way that you like. And provision IOPS allows you to basically set aside and reserve the I/O performance your application is going to need, and you can RAID these things together to drive even more performance across it. So if you're running high-performance workloads, CC2 is really where you want to be aiming. CC1 is perfect for Spot usage. If you're not familiar with Spot, Spot is a way of you basically controlling and naming your price for the supercomputing usage that you want to provision. So we have this utility computing platform, and we want to enable maximum utilization of that platform. We want as many people to be able to use it as possible because that improves our economies of scale. It allows us to operate more efficiently on our data centers, and we're able to pass those savings, as Andy was mentioning this morning, back onto our customers. Now, we do that in a couple of different ways. So we go to our hardware vendors and we custom design our hardware to make sure we don't have USB ports and things like that. But we also do it using various different pricing structures. So a certain amount of our capacity inside our data centers is filled up with reserved instances. This is guaranteed capacity that people reserve for up to 1 or 3 years ahead of schedule, and it's always there for them as and when they need it. And that, again, allows us to plan operationally more efficiently, and so we're able to pass on, in return for a small upfront fee, a lower on-demand hourly price for those instances. Then that fills up a certain amount in our data centers. Beyond that, we have on-demand access, so people spinning up the resources that they need as and when they need them. We have enough customers across the world that tends to equal out. So one customer's peak tends to coincide with another customer's trough. But we typically still have a gap inside our infrastructure, a capacity gap. And we want to be able to fill that as much as possible. So we actually allow customers to bid on that unused capacity and name your own price for it. You can jump up onto the website. You can actually graph the spot price. We recompute it every hour. You place the bid that you want to run your infrastructure at it. You can name it whatever you want. And you set your bid. As soon as the spot price goes beneath your bid price, will provision that infrastructure for you. The deal being that if we need it back again for any reason, the spot price will increase, and if it goes above your bid price, we'll take it back again. So you do have to architect for the fact that interruption can occur. Checkpointing is really critical with spot, but you can achieve significant scale and significant cost savings by running on this additional capacity. So CC1 is a perfect use case for this. CC2 you can get some great deals with. CC1 is absolutely perfect for spot as well. So couple that with provisioned IOPS, couple that with new instance types, which have a dedicated network back to the storage, you can start to build out some very, very high-performance systems. And on that, I would like to welcome your feedback, but also welcome some of the people that are designing and deploying these high-performance systems in the cloud to try and give you guys some insight into the workloads that we're seeing that work well. We'll try and get some hints and tips out there from some real pioneers in this area. So on that note, I would like to welcome up on stage Dave Fellows. Dave is the CTO at Green Button, and he's going to talk through what Green Button are up to, their background, and I think do a live demo.
Yeah,
fantastic.
We'll see how we go.
Thanks.
Thanks, Matt. Can I have the little clicker, mate? Thank you for seeing it. So hi, everyone. You could say our company, Green Button, was born out of the Lord of the Rings saga, where our founder, Scott Houston, was the CTO. Any Lord of the Rings fans? Yeah, cool. Got a few. Looking forward to The Hobbit, I presume. And so with 2 months to go to the launch of Return of the King, the final movie in the trilogy, they discovered that they had to build a brand new data center, a fourth data center, just to get that movie out on time. And so it was really, if I can click through, it was shots like these, the Battle of Pelennor Fields, where you've got thousands of characters that are individually generated by software and placed on that battlefield. And they estimated that to render a single frame was going to take around 600 hours. Eek. So they went ahead and built this brand new data center in a great rate of knots. IBM put the new blades onto a private jet and whisked them to Wellington in New Zealand. And they had a helicopter dropping kit to the site daily. It was quite an operation. And so they got this data center built in 10 days, which is a remarkable feat, I think. And this cost them around $5 million. Now, this is all for only around 5 or 6 weeks' work. And then this kit was actually going to sit idle for 3 years until the final production of King Kong was going to kick off. Bit of a waste, really. So it was realizing that there had to be a better way that was really the catalyst for what has now become quite a sophisticated software platform for managing big compute workloads across a variety of different clouds, both private and public. And Amazon's HPC platform is an ideal platform for a lot of these workloads, particularly those that have got large data requirements and heavy I/O, large data sets and heavy I/O requirements. And so Green Button have partnered with a number of ISVs across different industries. Pixar is a good example. We've taken their RenderMan software, enabled that to run in the cloud, and now that's available to end users as an on-demand service. And they pay a single transactional price, which includes everything, the compute, the storage, as well as the ISV's license as well. So that's pretty key, very cost-effective for those spiky workloads. So we're working in other industries as well, financial services, biotechnology, engineering, design. But today I want to focus on some of the work we're doing with Amazon and one of our partners, GNS, in the oil and gas space. And so GNS, with their product GloClaritas, a leading seismic processing software provider for the oil and gas industry. And so what happens in this oil and gas space is the oil companies, when they're searching for new oil, will drag these big long lines across behind these data acquisition ships and fire off small explosions and measure the resulting seismic activity. It actually looks a lot more like that, but that picture wasn't quite as attractive. So. And so from this, they can paint a fairly detailed 2D and 3D model of the ocean's floor, the subsurface of the ocean floor, and hopefully find out where that pesky oil is hiding. Now, the resulting data can be fairly massive. A typical project may result in around 50 terabytes of data. And so getting this into the cloud can be somewhat challenging. But never underestimate the power of traditional technologies such as FedEx. And so the latency is pretty rubbish, but the bandwidth is pretty jaw-dropping. And so we ship this stuff up into Amazon, and when it gets there, we load it into this Gluster file system. And Gluster is very cool. It's a clustered file system that you can scale out to support whatever I/O you need. And so depending on how many cores we're going to have to provision for this particular project, we can adjust the size of this cluster. We then have a visualization node. And so obviously when these guys run these, the end users run these jobs, we don't want to be driving FedEx trucks backwards and forwards. So the entire workflow lives in the cloud. And so the end users will connect to the visualization node remotely from either their workstation, laptop, or even a tablet device like an iPad. And through this, they can visualize the outputs and manipulate the data as they go along. Now, when they need to run up a seismic processing job and need the extra horsepower, they send the job off to Green Button through our REST API, and this virtual machine also hosts a cloud resource controller, which will dynamically provision these virtual clusters on the fly as the jobs come in. Now, these are MPI jobs, and so each job will have a virtual cluster provisioned with a head node and a number of child nodes. They'll do their work and save the results back into the cluster file system, and the users can visualize those outputs. So there's a typical project may run for a number of weeks, and what would normally happen at the end of the project is we'd have to ship all this data back to the customer because they have to keep it on their, keep it recorded or saved somewhere for a number of years. But Amazon recently announced their Glacier service, and we heard mention of that this morning. And this is really an ideal solution for this problem, where you just want to be able to move the data off to somewhere that's very cost effective, 1 cent a gigabyte a month, a perfect solution for this problem. So just a quick demo. So we're logged in here to the visualization node running in Amazon. And I was going to show you some of the nice visual outputs you can get from one of these jobs that I've run, but it wasn't playing very nicely in this low resolution, so you'll just have to use your imagination. But what I have over here on the right-hand side is another job that I've set up, a demo job. When I want to submit this to the cloud, I just right-click and select Submit. And this prompts me for my Green Button login details. And so this is a good example of where we work with a software vendor to deeply integrate with their application this interface into the cloud. So when the end users need extra horsepower, they simply click a button. In this case, all of the data is resident in that cluster file system, so we don't have to move anything around. But if this is an on-premise application, then it would also synchronize any data dependencies. So let's supply my login. And we can specify the number of processes which correlate to the number of cores that we need for this job. In this case, we'll just select 24. And this will go off, and oh, that's good, it's submitted. And if we flick over to the Amazon console here, we can see in this environment we have those the virtual machines that I described before, the resource controller and API, the visualization node, as well as a couple of instances for this clustered file system. If we click refresh, oh, there we go. So these are the 3 additional compute nodes, or the 3 compute nodes that we've requested to process this job. And once that work is done, it'll scale that back down again. So in the interest of time, we'll quickly flick back here. And so, what's one of these seismic processing jobs look like? How much compute does it need? And so a typical job running on an 8-core server may take around 1,000 hours to process. And in the oil and gas industry, it's, the competitive advantage is in how fast you can turn this data around and get the results. And so with Green Button and Amazon, we can run that same job and scale it across 4,000 nodes and have that run in a little over 2 hours, which is pretty impressive speed up. And you can run a number of these jobs in parallel as well, so you can really throw a lot of horsepower at this stuff. And we see this as fairly game-changing for this industry, as in others, and we hear that term game-changing every other day, don't we? But I think it really is in this case, because you have a lot of these small companies who have really smart people and really clever software, and now they can all of a sudden get access to this huge computing resource that would otherwise be outside of their financial reach and compete with the largest companies in their market. So pretty powerful. And with Green Button, it typically takes around a few hours or a small number of days to get a new workload or a new application running up in the cloud. So just to quickly show you some of the tools we have for managing and monitoring jobs. We can use this to monitor what the performance characteristics are like on the virtual machines that we have run up. This view is pretty cool. It shows us all the deployments we have across different cloud data centers globally. And so enterprises can see what they have deployed out in the cloud across their private and public clouds and get a snapshot of everything, what that's costing them, and drill into where that cost has been attributed. We have other governance features around chargeback and being able to set thresholds at different levels of an organization. This is our patented secret sauce, our job prediction, which is will be able to profile jobs, and our commercial engine then turns that into offers. So the end user can decide, rather than worrying about how many calls are spinning up, they can focus on, how fast do I need the results back, and what's the price point that I'm willing to pay, and find that balance. And we commit to that price point, so they pay no more than what's quoted to them. Cool. So thank you for allowing me to do a quick whirlwind tour of Green Button. If you'd love to hear about what you guys are doing in the cloud or thinking about doing in the cloud, and share some of our experiences and learning. So I'll be hanging around after this talk and floating around the Amazon booth as well. So thanks a lot.
Thank you, Dave. Yeah, we have to do a quick shuffle. So I think it's really interesting. One of the things that the cloud is kind of bringing up is exposing the cost of computational runs to the user and allowing them to make the sort of cost-benefit call on the run that they want to choose. So in Dave's example, exposing the cost to the user allows them to say, well, to me, this is worth running at a slightly higher cost to get the results back in slightly less time. And being able to achieve that with this sort of utility programmable model is very, very empowering. So we have our next speaker up here. This is Mike Driscoll. He is the CEO of MetaMarkets, and I believe you're going to do another demo for us, right? Yeah. All right.
I'm going to steal a dongle from you.
I'm going to get a dongle. Okay.
Yeah,
One second.
Good afternoon, everyone. Thanks for coming. As Matt said, I am the CEO and co-founder of MetaMarkets. And actually, like Matt, maybe for some background, I also have a background in bioinformatics, computational biology. And when I was in grad school, we invested quite a bit in hardware. I think like a lot of academics, we had a tendency to go out and buy big Beowulf clusters. And looking back, I really wish we had all of this AWS magic when we were spending millions of dollars with your tax dollars. We could have been spending tens of thousands of dollars a month with AWS. So today I'm going to tell a story about MetaMarkets and how we have been able to really achieve some dramatic results on AWS. And I'm also going to do as well, I will do a demo of our product. So I think there's a number 1. Is that what I hit? Great. Okay. And let's see if we can swap that around so you guys see a different view. Play slideshow. No. We'll see if we can actually. Okay, I think I'm going to see if I can try to get this to display. And we'll do mirror. Okay. Great. Perfect. So the title of my talk is Data Science in the Cloud, Lessons Learned with AWS. And MetaMarkets has been around for about 2 years. And our goal fundamentally has been to tame the inferno of the online ad markets. This is a space that we operate primarily in. And some of you may be aware, but every day there are upwards of 100 billion microtransactions that occur in the online advertising space. Many of the ads you see when you go to a site like the New York Times or the Financial Times, who's one of our clients, many of those ads are actually determined in real time through an auction system. They figure out where you're from, they have some idea of where you visited, and they try to target some advertising that is specific for you. So there's a lot of data, naturally, that happens when you've got 100 billion events a day. And at MetaMarkets, we see a meaningful percentage of that real-time stream. So what's needed when you're working with data of this scale? Well, certainly you need fast dashboards to operate over this high-volume data. You want to be able to, in real time, do aggregations over billions of events. You want to have flexible drill downs. And you would like, ideally, to have sub-second queries so that you can know, for instance, if in one of the cases we had, when GoDaddy had a DNS outage, several publishers were affected. Well, some of our customers wanted to know what's happening in real time. So this is kind of laying the table. And I guess it goes without saying that in this space, unlike in Wall Street, the value of these microtransactions is very low. Typically, it's about a few dollars to buy 1,000 ads online. So this needs to be cheap, right? This is where Amazon commodity infrastructure, burstable capacity in the cloud makes it possible to get analytics at scale without spending too much money. So we had a few solutions that we attempted. The first was your traditional relational database. Initially, we worked with Postgres, and then we used an MPP relational database based on Postgres. And the speed that we got with this was not sufficient. This is a picture of our stack. We think of our stack as really a 4-layered cake. We have ETL at the bottom. We use Hadoop. We also use Kafka increasingly today. We have a data store as the second layer. The third layer there, we have our own homebrewed analytics running. And finally, we've built some web-based visualizations at the top, which I'll show off in a bit. But nonetheless, this first solution was not fast enough. The second solution we had was actually what a lot of people do, I think, when they're building an analytical data stack. We used a key value store. So still we had Hadoop at the bottom doing our ETL, crunching data in hours, and we would store all of these pre-computed aggregations in HBase. Some people use MongoDB, some people use Redis, and this was good, but it had a couple of problems. One is, if you've ever built an architecture like this, the challenge is you have to decide in advance all of the possible aggregations that you care about. And while that seems okay at first, in some of our clients' cases, we have upwards of 30 or 40 dimensions that people want to aggregate over. What's the number of possible ways you can aggregate 40 dimensions? Well, it scales as 2 to the power of 40. It's a pretty big number. And you can take shortcuts, but it doesn't scale very well. The second issue, and this is even more of one, is that if you want to know what's happening right now, if you want to know how many people between the ages of 18 and 25 who are from New York, New Jersey, and California clicked on this ad 5 minutes ago, that information isn't available because it needs to flow through. You have to pre-aggregate it through your Hadoop pipeline. So we didn't really have real-time insight. And it turns out that data freshness is really important for folks in our space. So we thought, OK, that's not going to work. What we developed instead is we did something that maybe we thought was a bit crazy at the time, is we said, we'll roll our own database. And so we built something called Druid, and we presented this a few weeks ago at Strata in New York. We've open sourced this data store because we believe it's something not just that we can use, but many other folks out there might have an interest in. It is an in-memory distributed column-oriented data store. And the advantage is really twofold. One is it allows us to pour data into it through Kafka. So we do have real-time data available for querying. And secondarily, we don't pre-compute any of the aggregations in Druid. So everything is primarily stored in memory. And we're able to ask any question about any possible roll-up of our data in real time. And what makes this possible for us, frankly, is having the power of Amazon at our back. We have a 1,000-core cluster that we run today on Amazon, which our clients all have access to securely. And the nature of analytics often is that it's bursty. Not everybody shows up at once to ask a question of their data. And we think that cloud and multi-tenancy is a really natural fit to many of the analytics and data science challenges that people have. Unlike having a big box under your desk that you use once a day or once a week. So just some basic numbers for this platform that we're running. We look at over 1 billion events a day. We issue about 100,000 queries daily against that cluster, and the mean response time, to the extent that mean response times are useful, is sub-second. And that was really our goal. We wanted every single query that's run against our cluster to come back in milliseconds. So, to go back and say, we're not sort of breaking the laws of physics here, right? What are the principles of the performance we get? First, memory. We all know memory is much faster than disk, about 1,000 times faster for reads. Lately, we've been looking at using SSDs to back some of our stuff as well. Parallelization. Because we have thousands of cores accessible to us, we get, typically data is not striped across all of those cores, but we get a pretty high parallelization factor for our data. And then the last piece, and of course we distribute the data across many nodes as well to get that parallelism. The last piece is we do some summarization. So we tokenize and compress the data we receive, and that reduces its overall footprint. Because we're column-oriented, we're not pulling entire records out and scanning full records. We're looking only at a particular attribute of a record, and again, that gives us a little bit of a speed up in terms of our ability to look at lots of data quickly, interactively, and in real time. So, really, one distinction we feel for this infrastructure that we've built on top of Amazon is that we built it from the ground up to run on the cloud. And this has given us a few nice things. Certainly, it's elastic. When we've had customers come on board and start pouring lots of data into our system, we can move our overall capacity up within hours to support that. We also have borrowed a lot from the Hadoop ecosystem. We use Zookeeper to track where all of our data is living, which segments are living on which servers, and we have a replication factor for our data, which gives us some fault tolerance. So, right now, for instance, we're able to do rolling restarts for all of our machines. We don't have to have any downtime for our cluster. We can take nodes down, and yet our service maintains its reliability and its performance. And then finally, a lower total cost of ownership. I mean, frankly, the type of power that we provide to our end users is something that very few of them could afford to buy on their own. So any one of our clients would not be interested in paying the bill that we pay to Amazon per month. But distributed across many of those clients, they're able to achieve some real high performance computing power, but at a fraction of the cost of what it would cost to have it on-site or on-premise themselves. So these are the 5 key features of Druid. I did mention this: distributed column store, real-time ingestion, fast data scans, fast filtering, and it's operationally simple to deploy. That picture is a picture that the lead architect of Druid insisted we put in this talk. That's his apparently what Druid looks like to him as our mascot. And then some benchmarks. So typically what we see for scan speeds are 33 million records per second per core. We've got ingestion rates of up to 10,000 events a second that we can take in. Again, these are real-time advertising markets, so we get pretty high QPSs there. And then just one data point for a cluster we're running: 100 nodes, 6 terabytes of addressable memory, 400 terabytes on disk, and we can do a query over 6 terabytes in memory in about 1.5 seconds. So it's really possible to get some great speed here. I don't think we have numbers that will go above what Matt gave for the 240 teraflops, but if we had a big enough budget, maybe we could try to give you guys a run for your money. So with that, I think what I'd like to do actually is pop over and show a demo of the system. Okay, so what I'd like to do here, if we can bring this up, I'll have to resize this, is actually show the MetaMarket solution at work. And one of the things that's great about working inside of a cloud ecosystem is that we think cloud services play well together. So for instance, many of our customers are actually already on AWS. And the way that we bring data from them is typically through the cloud, through S3. So what I'm going to actually do here is I'm going to do a demo of actually showing the ability for us to pull data from an S3 bucket. So let's see what happens here. Okay, so you can see we say here in MetaMarkets, everything begins with data. Connect to your data to start exploring right away. And this is something that we're using internally right now to pull people on board. And you can see here, we ask a few questions about your data and how you'd like to connect to our overall dashboard. Here I'm going to choose an S3 bucket. And I'm actually going to, let's see if I can get this right. I'm going to specify actually some FAA flight data that we've pulled down. And if you wanted to create your own key, you could create that such that only MetaMarkets had access to it. We've done that here. And then I'm going to say next configure data. And so what we're doing here is we're actually sampling down data off of an S3 bucket. We're automatically detecting the different data types that are in this CSV formatted data. And we're looking for a timestamp. That's pretty critical for us at MetaMarkets. And here, if I click Show My Data, we're actually able to prepare, load, and ultimately index the data that's in this bucket and show you a preview of what you'll get back. And like every good cooking show, okay, I'm going to pull off a few of these guys. You can see here what we're looking at is actually flight information for which flights, flight times, airlines, origin cities, and effectively we're allowing you to bring any type of OLAP data into our dashboard and immediately get visibility into it. So I'm not going to go back and play too much with this data set, but I just want to give a sense of what's possible to do when you're in a SaaS ecosystem and when you're already working on Amazon. Another example that I'll give, and this is really getting to more of our core use case, here I'm showing an example of our dashboard at work for a demo of a particular real-time bidding exchange. And what you can see here is, if I resize this appropriately, you can see the number of impressions and the amount of revenue that's being driven by this particular exchange. About 4 million in revenue and billions of impressions. And as I select different attributes of this data set, each click is adding a different filter, and each click is actually causing a real-time query to be issued against that backend. So I can go back and look at 4 weeks worth of data. I can zoom in for a particular week. I can look at a particular day. And every one of these queries that I'm running here are happening in real time on the Amazon cluster that we run. And that's a pretty powerful thing for us. It allows us really to, allows our users to ask really any questions that they would like of their data. Here I'm showing an example, again, sizing appropriately of some visualizations that we allow, a real-time heat map looking at a distribution of pricing by country. And then we've also got some data that we've collected from Wikipedia. And here actually I can show on Wikipedia, we can see what are some of the top most edited pages by country in the last day. So here I'll say for the top 5 countries that are being active on Wikipedia, what are some of the articles that are active there? I can interactively specify a language here and say, let's look only at English languages. So you can see Canada, Ireland, Mexico, the United Kingdom, of course, are the most edited in terms of English language countries. But really the power here is that there are hundreds of millions of events underlying this data and this data set. And we're able to pick and choose and click and slice and dice over this data interactively. And this is being updated within 6 seconds of anyone making edits to any web page across Wikipedia. And the same goes for any of our customers. We're able to give them insight into their data that's as old as 10 seconds ago. So really that's kind of what I wanted to show off in terms of our product and really why I think it's been tremendously useful for us at MetaMarkets. And with that, I'll say thank you and thanks all of you for your attention. Thanks very much.
Thanks, Miguel. Alrighty, fantastic. So I think we've seen some really good examples here of what you can achieve in terms of delivering scale to either your internal customers or your external customers in delivering the sort of performance, particularly around very, very large data sets. And I think that's pretty much all that we have time for. So if you have any questions, I welcome you to join us at the front here. We'll also be at the booth, and we'll be delighted to answer any questions that you have about this or anything else related to AWS. Thanks a lot, guys.